So today we're going to talk a little bit about data structures, and we're going to touch on data mining. Data mining itself is a hugely complicated and massive topic, and we are going to spend about 15 minutes looking at it, and then you're going to come back to it in the practical. So it's a question of familiarity with these kind of things. And if you have any questions or spam it, say, you can ask them on QChan, and we'll check at various points. So I'm talking a little bit about hierarchies of data, a little bit about how we structure data. Data is really complicated and increasingly important. The amount of data that we capture in your average, organization is absolutely huge. We talk about big data. Most organizations, the data that they hold 5 or 10 years ago would have been called cutting-edge levels of big data. You look at, say, the volume of data Queen's holds, the amount of logging information, the amount of records that we hold, the amount of contact transaction information, that kind of thing. Data is everywhere. Data is huge. So we're going to talk a little bit about the structure. So when we have huge amounts of data, really we try to worry a lot about how we structure it. Because unstructured data is incredibly problematic. The world is full of lots of unstructured piles of data. And data really is only useful as we can make it. It's only as useful as the information that we can pull out of it, out the other side. And if data is unstructured, we can't pull anything out of it. It's luck more than anything else. If we have just a pile of files, we have no sort of filing system. If it's anything like my filing system, you throw everything in the corner. It's bad enough. For large organizations, it gets bigger. And if it's hard to find, we can't turn it into information. Data is the raw source. Information is the thing that makes us happy, thing that lets us know. And it's also incredibly hard to sort, search, query, and exploit. So one of the big challenges that's still open in the world of data is things like data mining fill in, is we have organizations, individuals, countries, whatever, that hold huge volumes of data, but they don't really know what to do with it. So if you look at a company like Facebook, Facebook is very good at two things. It's very good at getting data from you. We all, well, maybe not all of us, but most of us willingly go on and we tell Facebook who we know, what we like, where we live, where we've been, all of these kind of things, let alone what we tell Google when I walk around with my Android phone. But what these companies are very good at is being able to actually exploit that, is being able to take this huge volume of data that they capture from us and turn it into meaningful patterns. And so if you take a company, say like Google, I carry my Android phone around with me. What might I be interested in? What shops do I want? How busy is the road that I'm driving along? Because other people have Android smartphones, and I haven't just stopped, everyone else is. So we can capture this, and we can do it. So the reason why they can do that is because they've thought very long and very hard about how they structure the data that goes into it to make it meaningfully exploitable in order to go. So we need to think very carefully about how we structure data. And when we structure it, we talk about how we organize it, sure, but also how it's structured in relation to other elements. And this comes back to what we were talking about last week, the relationship between entries in the database, because we need to map these relationships in a meaningful and useful way to represent the data, because that allows us then to exploit it and to find the links within it. So one of the most common ways of storing data, and it's still popular, still used in most file systems, is the hierarchical structure, where we start with an item and we have parents and children. So things go down, they come from a parent, they go down to children, and each node may have 0 or more children. Each child has one and only one parent, with the exception of the root node that is the only node that has no parent. So we have here a lovely categorized, organized data. This is a graph in graph theory terms. And if you go on to do, and some of you may already know quite a lot about this, if you do things like machine learning, you look at graph theory, they love these kind of things because it's brilliant, it's great. And in fact, a lot of structures go even further. So there's a thing called the binary tree, where every node only has 2. It has 0, it has 2, so you can follow it down left and right leg. This is a wonderful structure to exploit. You can write code really easily to walk through it. We know where to start. there are definitive dead ends. There's only one path from left to right touching all the nodes. It's really easy to traverse. It's really easy to exploit. And that's the relationship that goes in. And this hierarchy structure is very popular because it's used in file systems. Folder, a C drive in Windows or a root mount in Unix, and that is what you put in, and all the files go below it. But there are significant limitations to how we want to represent this kind of data. So if we have, for example, a module, CSC1023 here, and we have our students, our lovely students, Alice, Bob, and Kaz underneath it, and they're linked to this module. They are children of this module. God, that's awful, isn't it? Welcome, you're all children of this module. I try and sue for a separation now. So we have this, that's fine, okay, that's great, and it works very well when we have other modules, we have children underneath it, we have stage one, so you stage one, this module, this children. The problem, though, is that with this straightforward hierarchy, we can put Dave, Eric, and Fiona in 1024, but what we can't do with the standard hierarchy is find any way of putting one person under multiple parents. So it works theoretically, but actually, most of you are children of many modules. So there needs to be some way of kind of trying to map that around. And what we actually have is the model here between student and module is a many-to-many relationship. And many-to-many relationships are very common in the real world. You know, data works very well. Humans, you know, regularly interact on a many-to-many basis. You know, I have many friends, they have many friends, we're not necessarily in the same group. You know, I teach many modules are taught by many lecturers, all this kind of stuff. So it often ends up with quite a complicated system. Now, one of the ways that file systems get around this is by using shortcuts. So file systems very easily let you exist in more than one place, under more than one category, more than one folder, by creating a shortcut that leads to the actual file there. And we could apply that to databases if we wanted to. But the problem is when we start introducing loads and loads of shortcuts and file systems and paths around, it then becomes really difficult because we've taken a very clean, nice structure that's really easy to understand, easy to use. And actually, if we put all these shortcuts and hops and workarounds in, it becomes very messy very quickly, and we have the same problem we originally had. So the advantage then of a hierarchy is it's really clean. It's clean, it's logical, it's really fast to search, to navigate. Little duplication. Even metadata is stored in one node, and we use shortcuts between it. Everything in its place and a place for everything. So we know where everything goes, and it fits in nicely. But it often fails to model what we want it to model. It fails to actually model the real-world data system we're hoping to put in. And we end up with a whole bunch of workarounds. And those workarounds tend to be more complicated than the problem we were originally trying to solve. So we end up with a very problematic issue. So how do we overcome that? So another way of thinking about it is rather than everything being in a tree with roots and nodes and parents and children, we can think about data as being within sets. And this is set theory that some of you will have come across in mathematics. This is set theory, light set theory. Is that still working? Yeah, okay, still on. Very light version of set theory. So a more flexible solution. Is that working? Can you hear me at the back? Yeah? All right, sorry, I'm going mad today. It's been a long day. A more flexible option is to think about data instead of this hierarchy in collections or sets. And the idea is that an item of data, a node, whatever you want, can belong to 0 or more sets, and a set can contain 0 or more items. So in this case, we would have our students available as nodes. We go through, put them on, and we would create all of the nodes within the system. We would happily have a set, CSC1023, that these students belong to. We have another set, 1024. These students belong to it. But critically, because there's no relationship, there's no hierarchy, it allows us to link someone to more than one set. So we can have nodes and items which are members of no sets, 1 set, 2 set, 10 set, however many you want to do in order to work the relationship between them. So that allows us a much more flexible way of modeling data that it comes into. And it's quite commonly used in most real-world relationships. We talk about many-to-many relationships. Most of the time, we're talking about some sort of set theory relationship between it. So we can represent data sets in a few different ways. So we look at a visual representation as we take a node and we have a boundary of our set on the outside and all of the nodes within it. And we can then create something like a Venn diagram where we put in another set of nodes, and we not only have our two sets, but we have an area of overlap between them. We have our nodes between them in order to overlap in the middle. So in this case, we'll talk about A and we'll talk about B in order to go in. So we can define them like this. We can define them visually. In terms of written notation, we tend to define them like this with curly braces. We say set X contains members 1, 2, 3, and set Y contains members 2, 3, 4. So that's how we write them down and we do it. Now, one of the powerful things that we can do with sets is we can use operators on them. So we have a set, and all a set is a bunch of stuff, right? It's a collection of nodes. And we can use some set operators which allow us to determine what subset we actually want to come out of these, which nodes we're interested in. And the three general logical operators we use are the union, the intersection, and the set difference. Now, this is all theory. This is all theoretical, and we'll look at it, and you will be looking at it in theory this week and in the practical. However, in a few more weeks, when we start looking at SQL and we start looking at ways of exploiting data from databases and we start joining tables together and doing left joins and right joins and this kind of thing, this stuff will suddenly, hopefully, you'll see the practical application of it. So the result here, when we have sets and we use a set operator, is the result of items that match the operator. So the union is the set of all the items that are a member of either or both of the sets. So here we go. Here's A and B. The union of A and B is nodes which are a member of A, a member of B, or a member of both. So union, very simply, is the sum of the two sets. If something's in both, we don't duplicate it. It's in there, but it's the sum of any number of sets which is included. So if we have mathematical 1, 2, 3, 2, 3, 4, the union of 1, 2, 3, and 2, 3, 4 is 1, 2, 3, 4. So fairly simple. All of the nodes that are included go into it. The intersection, conversely, is the items that are members of both sets. So only items that appear in both sets. So in this case, it will only be the intersection within the Venn diagram where both set A and set B overlap. Items which are members of set A and set B will appear within that intersection. Likewise with notation, 1, 2, 3, 2, 3, 4, we will end up with the intersection of X and Y being 2 and 3 because those are the two node items that appear in both sets. Not rocket science, hopefully with me so far. The last operator we use for sets is the set difference. So the set of items which are members of one but not of the other. Effectively, a subtraction. Take a set, subtract any of the elements in that set that appear in this other candidate set, and the result will be the set difference between the left and the right. So the set difference here between A and B is the nodes in A that do not appear in B. So we are subtracting from A everything that appears in B. In this case, these ones don't even appear in A, so they don't matter. But the nodes in the intersection are taken away from it out of the other side. So the set difference is give me the things which are on the left-hand side but not contained in the right-hand side. Unlike union and intersection, set difference is the only one that makes a difference which way round you go. So the set difference A to B is different than the set difference B to A, as hopefully will be fairly evident. And in notation form for your reference, we do a set difference, 1, 2, 3, 2, 3, 4. We find 1. 1 is in X, it is not in Y, it is the only member of X which is not contained in Y, and voila, off you go. And as I mentioned, if you do it the other way around, B to A, as you'd probably expect, because we're taking the set of B, we're taking away what's in A rather than we did before, which was A to B, and we remain with the items which are only in B and not within A. And there's another slide showing it as a difference. All right? So these things are useful to know, and as I say, it will hopefully come down when you start working with tables and you start working with complicated SQL queries in order to do it. And of course, it is entirely possible to use these with multiple sets. Is that we rarely do we have a simple example where we have two sets and they have an intersection. We're usually dealing with many, many sets, different characteristics. So I want the list of students who are in CSC1023 are also one-legged, have a blue jumper on, and, you know, Tuesday is their favourite day of the week, whatever. You can just start putting sets, you put students into sets, and you can intersect all these sets together. And obviously this will contain students which are the intersection of A, B, and C. A and B, B and C are A and C, and so on and so forth. So you can use all sorts of different combinations in order to go in. You can also use brackets in order to do it. So let's have a quick go. We'll take a few minutes to have a look at this. So here are three sets, X, Y, and Z. The intersection of X and Y, the intersection of X and Y and Z, the set difference of X and Y intersected with Z, the set difference of X and Y unioned with Z. So have a quick go on those, and we'll give you a couple of minutes, and then we'll come back and have a look at what the answer. Okay, how are you getting on? I fixed the microphone. I apologise. I did ask. I thought it wasn't working, and I obviously didn't. Someone nodded at the back when I said I didn't check the chat. The reason I have two microphones on, which seems to be an area of some concern, is so the head of school can monitor what I'm saying permanently in case I say anything completely inappropriate. No, one of them is recording. So there's no way of just plugging into the output, and if I use the inbuilt mic in the Mac, when I do my wanderings, you tend to, so one is for that. So just let me know, please. I appreciate, I'm not looking at this live. If the mic conks out in future, people start waving or throwing something, okay? Because I will just carry on with it, because it's really hard for me to hear. There's no feedback from it, all right? So I just assumed that I was still fine. So I apologize to those at the back who couldn't hear me. Yeah, the selfie, it's really disappointing, the selfie. We will do another one. Should we do another one next week? We'll do another one on Tuesday instead. I can post it, but, you know, it's deeply upsetting to me. Some people asked some other questions. No, I think it was mostly terrible stuff. Okay, right. Yeah, these batteries always run out. They buy the world's cheapest batteries, and then they don't refill the safe. And then when you ring them, I rang them once and said, there are no batteries in the lecture theatre. They said the students have stolen them. So that's good. Okay, so let's have a quick look at this then. So the first set, the intersection between X and Y. Who has an answer for that? Someone shout out. I can't bother to use technological things. What do we reckon? Sorry? Jim and Tom? Yeah? Okay, yeah, absolutely. So we're after, with an intersection, elements that only appear in both sides. So Jim and Tom are the only two nodes that appear in each side. Intersection of X and Y and Z. Tom, yeah, just Tom. Okay, so really simple notation. We start putting intersections on. It doesn't matter which way with these we bracket it. We could put brackets in, but it doesn't matter if we make subsets. Right. This one, number 3, the set difference between X and Y, intersection with Z. So let me just have a quick look at that. Sorry, go on. Alice. Set difference between X and Y, Jim, Tom. Yes. Well done, thank you. I don't know why I'm looking at it. I've got them here. Right, okay. Alice, yes. So we take away the elements from X that are also in Y. So we take away Jim, Tom, Joanna's not in there, so we're left with Alice and Bob. We then take that as a median set, because we're using brackets, we intersect that with Z, and the only common item between those two sets is Alice. Okay, so 4, set difference X and Y, union with Z. Who wants to make a stab at that one? Yes, absolutely. No, hang on. Yes. Yes, Alice, Bob. Yeah, yes, sorry. Lost the plot. Alice, Tom, Bob, and Agatha. Yeah, okay. Very good. Excellent. All right. So we'll be going back through this again in the practical on Monday, getting used to some set theory. We're not going to do it if anyone's done proper, complicated, real sets. We're not going to get to that level. This is as far as we go in mathematical set theory and set notation. But it's useful just remembering this idea about here is one collection, here is another collection. What are the descriptors I can use to describe the output set that we use? We use those in combination with each other. Right. Has anyone got any burning questions on set theory? In here? You can hear me now, hopefully. I could use a headphone/mic splitter cable to stop using double batteries. A headphone port and all that would go into Mac. Just in case, whoever that is, I've tried. I've tried all the combinations, trust me. You can probably solve it, but I can't. Anyway, right, good. So let's move on then and have a quick look at data mining to finish off. And we'll finish slightly early again today because it's a miserable, horrible day. So as I mentioned to you, data mining is really a module on its own. In fact, it's a course on its own. You could have a degree on data mining. You could certainly do several full modules on it. So we're going to have a very brief taster about it. So it is a normally a computerized process, you can do it manually, to discover patterns in data, usually large data, using combinations of techniques from machine learning, statistics, and databases. So it's taking a series of data and trying to mine it for real information that we can pull out of the other end. And there's a process, the universal process that's followed. First one is that we need to pre-process our data. Real-world data is notoriously messy, called dirty data, but not that kind of filth. Real-world data is missing bits, it's wrongly coded, it goes through. I've done a few bits and pieces of work where we work with the NHS, and health data, you're capturing at hospitals, you'd think, okay, it's going to be reasonably good. It's not, there's huge volume. Did that person die? The entry stopped, they've created another file, they've done these things to see from the time pressure. So the first thing to do is to try and assemble it and cleanse it. So remove noise, fit in any missing data. And fitting in missing data, we could have a whole course on that itself. With climate data, we use estimations between peaks within it to do it, and then climate deniers will say that we're fudging the data in order to do it using industry standard techniques, but that's by the by. Once we've got the data and we've cleansed it and we've got it ready, we then go through the process of data mining. So the first thing we do is we look for any anomalies within the data. We look for glitches in the matrix. We're looking for unusual records, errors, things that may be interesting within it. The second thing we look for is we look for associative rules, association rules, so relationships between variables. If, when somebody is checked into A&E, it is Saturday or Sunday, are their outcomes, the likelihood of them surviving, drastically affected? Try and find the simplest thing that impacts everything. Right? If we did a statistical study of car crashes and severity of injuries, we'd probably find that speed made a big difference. When you crash, if you crash at 90 miles an hour, you crash at 9 miles an hour, there is probably a straightforward correlative difference between them. We then start looking at clustering. Okay, so can we find groups of objects that have similarities within the data? Can we find things or indicators and variables that are similar in terms of their output? Can we find a regression model? Can we find a linear regression model or another regression model that fits the data, that we can run against it, that allows us to work forward? And then finally, we kind of summarize the data, some kind of compacted, visualized representation of reports, and then we validate our approach. So like all scientific method, this relies on the thesis approach. We have an idea, we check the data, we make a prediction of the future. Now, that might be a genuine prediction. I've got all the data until today, and I'm going to predict what's going to happen over the next 6, 9, 12 months. Usually what we do is we don't go until today. If we've got the data for the last 30 years, we use the last 25 years of data to train the system, to look for patterns, to do this, and then we test it against the next 5 years to see if what we predicted 5 years ago happened over the last 5 years. It allows us a much quicker way. We have a training set of data and a testing set of data to validate. So some of the issues that we face when data mining widely is having suitable available data at all. Have we got data in sufficient detail, in sufficient quality, with sufficient levels of granularity to actually allow us to answer the question we've got? Increasingly, we also face privacy concerns. It's not uncommon now for privacy to actually be people listing as the #1 issue in terms of their concerns with using stuff online. We've recently had the Cambridge Analytica scandal where Facebook had their API abused by a company that would got all this data out, and they would have used data mining machine learning techniques in order to try and predict who was likely to vote one way or the other. Interesting thing about that, if you follow that kind of stuff, is that the learned people, not me, people who know what they're talking about, are fairly convinced it didn't really affect anyone, it didn't influence anyone. All they did was target people who were already voting in one way or the other. But, you know, that's by the by. Nonetheless, privacy concerns, people get very worried about computers knowing them. And this is especially true with people that don't really understand computing. Older people, vulnerable people, whatever, tend to think computers are better than they are. We know how useless they are. You ever try and use a Google Home and you have a 5-minute screaming conversation with it because you want it to turn the light on and it starts playing, Spice Girls music. I'm not that worried about the automaton revolution, but privacy concerns are a huge thing. If you say to someone, what are you going to use the data for? I'm going to data mine you. I'm going to learn everything there is to know about you, and then I'm going to use it to target you with shopping. People tend not to get involved. We have issues of processing power. We have all this data. Great. In theory, if we had an infinite number of processors, an infinite number of processing worker threads, we could do whatever we want with it, but we require something to do it. And how accurate is the training or the baseline data that we get out? One of the biggest problems with machine learning and data mining is what's called overmatching. If I have a set of data and I train my system on it, and I'm really good at training it on it, and I tweak my algorithm so that this predicts what happens here, maybe all I've done is create an algorithm that really accurately turns this into this. I don't know whether I can predict it or not, so unique things. And of course, we're always open to the possibility of false patterns or findings, because correlation is not causation. We often can find things. If we just look for patterns, we'll see them, but they don't necessarily mean that it's true. So it's a graph of the letters in the winning word of the National Spelling Bee versus correlated with the number of people killed by venomous spiders. So we can be pretty sure, if we looked at this, we see a reasonable pattern, there's some variation, but as the number of letters increase in the word spelling bee and decrease, the number of people killed by venomous spiders goes up and down as well. Now this is obviously a specific example chosen to show the ridiculous nature that if you run machine learning long enough and you say, examine all these variables and find a link or a apparent causal relationship between them, you will find something ridiculous. But when we're looking at smaller data sets where we don't have such diverse variable bases, we often do come across mistakes to be made. So in the real world, data mining is used very, very widely. Finance love it, medicine love it, insurance, economics, business, engineering, you name it, machine learning is being used. Often when people say AI, what they mean is machine learning, analysis, and prediction. They don't mean anything that clever. It's just going to go through, and through a series of simple tests that computers can do because they can look at millions of data points, we are able to make reasonably learned guesses about what happens. So the kind of process that we would go through is if we had an attendance sheet like this. We have a bunch of variables on top. Some are discrete, some are categorical. So days, times, was it raining, was it snowing, was it windy? And then a categorical figure for attendance. And often we use categories rather than numbers because we want to be able to put things in bounds because it makes it a little bit easier in order to do. And so the challenge would be, if you were machine learning this, you'd have all this data and you'd say, okay, what is it that influences students attending lectures? What is it that's the most likely predictor that we can use? So we start by looking at variables. So we say, okay, look, here's an easy one, day of the week, right? So we have three weeks. So we've got 3 Mondays, 3 Tuesdays, 3 Wednesdays, 3 Thursdays, and we can look through and we can see what comes out the other end. You can see that we have Monday attendance medium, low, medium. We have a high attendance on Wednesday. We have a medium attendance and then a medium attendance. So there's not really a great correlation between day of the week on its own and this. So we just start looking at more and more variables. We say, okay, well, what about the time of the lecture? And again, 9 a.m. lecture, we're medium, low, medium. Now, you can tell this is fake data because if it was real data, 9 a.m. would immediately drop off. Really obvious. Really obvious. You know, how drunk they were the night before, how low the attendance was in the morning. But we go through and we start looking at these kind of things. Is rain a factor? On the days where it's raining, where it's not raining. So we have a variety of changes. What we'd probably do is we'd try and find another set of variables that fit. So, for example, we'd say, okay, look, we've got samples from Wednesday at 1 o'clock. We know that those are the same. And then on different days, we have different rain. So it didn't rain, it did rain, it didn't rain. High, medium, medium. Again, no correlative value. And we go through like that. We start looking at more and more values. Snowing. Okay, so snowing, interestingly, snow joke. Come on. That's the high point of my jokes this semester. I feel I've peaked. That's why I put the batteries back in the mic, was for that one joke. So, you know, snow we have a look at. Okay, so the no's don't really seem to mean much, right? No doesn't mean that much, but the yeses do. So now when we look through, we say, okay, well, look, the 2 low attendances were on days where it was snowing. So snow then apparently becomes a reasonable indicator. What we can do then is we can move back and we can say, okay, let's identify blocks of other ones, where there are differences between them. Are there combinational things we can use? And in the chances are, our prediction model would come out with something like, if it is snowing, there will be low attendance. If it is rainy and windy, the attendance will be lower. And we look at things like this. We look at individual variables. We look at combinations of variables. We look at what are the things we can use in order to predict it. And once we've built and we trained our model on this, the next thing to do would be to sit back and wait and see what attendance did when we tracked it further on. Is this, if I made these predictions, do you think this would be an accurate way of predicting attendance? On one class, using 3 weeks as training? Probably not. It happens to be winter, it happens to be cold. Sure, it snowed on those days, but we've only got 2 days where it snowed. Did something else happen? Is one of those lows irrelevant to it? Was it a massive party the night before on one of those? We just don't have enough information. But as humans, I can look at this and we can have a look. If I said to you, oh, I've got 10 years of Queen's attendance data, 10 years of Met weather reports, 10 years of news reports about Holy Land parties that went on for 3 days, students didn't come in from, news reports of people falling out of windows, the heroes of the Holy Lands. That probably would be enough data that we would say, yeah, okay, we've probably got enough data now that we might be able to make predictions, but you know what we couldn't do? We couldn't bloody analyze it. We couldn't realistically sit here and go, oh, this one, you know, it just doesn't work. But we can make a computer do it. So that's where computers come in, and that's where computers are very, very useful. Someone's going to take their dongle out. Okay. How do I live with all those dongles? Look, we're living in the wireless revolution, and I'm a Mac fanboy, right? Which means that I carry a tiny Mac with a bag that weighs more than me around with me, containing every single possible connection and combination, all right? And that Mac was definitely value for money, so don't tell me otherwise. Snow joke, yeah, good, well done. Right, so look, I think what we'll do then is on Monday you're going to cover the data sets, data mining, you get a little bit used to it. I will thank you very much for your time. If any of you have any questions, pop down and see me, and I'll see you all on Tuesday. Have a lovely weekend.